So I don't like to stand here, so I prefer to talk and to walk a bit. I don't know if it's right to use the microphone. Can you hear me like that, or it's better with the microphone? No? Okay. Yeah? Better like that? Yeah, okay, I will use it. So thanks, Eduard, for your kind introduction, and I would like to start thanking to the DCIS organizer and to the General Chair for inviting me to deliver this talk today at this conference and giving me the opportunity to share my quantum journey with you in spite of such long titles. Sorry for that. I promise my presentation will be much shorter, or at least in time, right? So, yeah. So I would like to start my presentation by sharing one of these old stories from the past. So the first conference I attended was DCIS, but back in 2010 when I started my PhD. And I have to confess that the day that I have to give my presentation, I was like very anxious. I was like shaking. I mean, I could hardly stand on my feet, like sweating, and I thought I really was going to faint, right? Hopefully I didn't. I didn't faint. I managed to deliver the talk and to give, I don't know how good it was. Maybe it was like horrible. I don't know. But yeah, but I did manage. And this morning when I woke up, I had the same feeling. I was anxious, but it felt different. It's this kind of anxiety because I'm very excited to be here again in this conference where I started my research trip. So it's an honor for me to be here. So thanks again. So let me start like just talking about where I work. So as Eduard mentioned, I work at Delft University of Technology in the Netherlands. I work in this high building here that is the Faculty of Electrical Engineering, Mathematics and Computer Science, and I work at the Quantum and Computer Engineering Department. But I'm a assistant professor there, but I'm also one of the PIs of QTech. That is here in the Faculty of Physics in TU Delft. So this QTech is an advanced research center for quantum technologies, and there most of the people working there are physicists developing different technologies for implementing quantum processors of qubits. Within QTech, as you can see here, we have different roadmaps that they are divided depending on the technology that they use and also on the goal of each roadmap. For example, we have the topological quantum computing that is based on a technology that is called Majorana's, and they didn't build a qubit, they built one. So once they saw like a topological qubit, but they're still trying to find it again and to build it. But Microsoft, there we have what they call a Microsoft station, because as you may know, so Microsoft that is one of the main companies investing in quantum. They also have QS stations in different universities, and we have one here in QTech within TU Delft. Then we also have the QUIN roadmap that stands for Quantum Internet and Networking, that the goal of this roadmap is to build a quantum internet network connecting different cities in the Netherlands. And the roadmap I belong to is the fault-tolerant quantum computing. So the aim of this roadmap is to build a full-stack quantum computer that is capable of performing fault-tolerant computation. And I will elaborate a bit more about that during my presentation. Within this roadmap, we work on two main technologies. So it's silicon spin qubits. So those are qubits that are built using like normal regular transistors, but just trapping an electron there, and also superconducting qubits. And within this roadmap, as I say, as we want to build this full-stack scalable quantum system, we have people working on the devices themselves, but also in the different layers, engineers working on the different layers of the system. That I will go through that later. So, and yeah, as Eduard mentioned, we work in close collaboration with the Intel. We started like now 6 years ago. So yeah, our research is together with people in Intel. Now, why we want to build a quantum computer? So a quantum computer promises to solve some complex problems that are intractable for even the most powerful supercomputers that we have nowadays. What kind of problems are those? So quantum computers will be very good at quantum simulation. With those quantum simulations, you could model in new chemical reactions and also to develop new materials that, for example, developing harder polymers for airplanes or more efficient materials for solar cells, or even developing or synthesizing new drugs. They will be also very good at solving optimization problems. And in this sense, we are taking, like we say, a hybrid approach in which you have like classical optimization like solvers working together with quantum solvers. And those optimizations have applications in improving different products and services from different kind of industries, that, for example, logistics, healthcare, or finance. Now, one of the most promising and the most popular, let's say, application that you may have heard of is in security, or in encryption decryption. So it's said that if we build, at some point, if we are capable of building a quantum computer, we will be capable of breaking one of the most widely systems used nowadays, that is called RSA, and is based on the factorization of large numbers. So there are indeed already people working in what they call post-quantum cryptography, that is developing algorithms for security that a quantum computer will not be able to break. And for that, what we use is what we call a Shor's algorithm. Now, what is quantum computing all about? So as you know, the basic unit of information in classical computation is a bit, right? A bit can be either 0 or 1. So in quantum computing, the basic unit of information is called quantum bit or qubit. A qubit can be either in state 0 or 1, like a classical bit, but it can be in 0 and 1 at the same time. So it can be in both states at the same time. And that is what is called superposition. This superposition is described by this mathematical formulation here, in which it's just a linear combination of these two states, 0 and 1, related with these two alpha parameters. Those alpha parameters, in some way, what they express is how much your qubit is in state 0 or how much your qubit is in state 1. Okay. But if you want to read out the information, if you want to measure the qubit, you cannot read out that superposition. You cannot read out this alpha 0 and alpha 1. When you measure the qubit, what you get, it's a binary value, either 0 or 1. And the probability of getting 0 or getting 1 when you measure your qubit out is given by the modulus of a square of alpha 0 or the modulus of alpha 1 square. So in other words, what you get at the end, it's a binary number, either 0 or 1, given by those probabilities, and on top of that, you collapse your qubit to the value that you read out. So if I measure a 0, my qubit is collapsed to 0. If I measure a 1, my qubit is collapsed to 1. So I destroy the superposition. Okay? Now, so I guess that is clear from this measurement example that I just explained, that quantum is measuring and quantum computing is a probabilistic way of computing, and I will emphasize that in the next slide. Now, where the power of quantum computers comes from? So the power starts when you start combining qubits. So imagine that now I have a system with 3 qubits. So the state that requires this system with 3 qubits is described by this equation here, that if you look at the state, it contains all possible combinations. So it goes from 0, 0, 0, 0, 0, 1, 0, 1, 0, and 1, 1, up to 1, 1, 1. And for describing that, you need 8 different parameters to express this system. So in other words, a qubit is a system composed, but n qubits can hold up to 2 to the n values. So imagine that you're capable of having like 50 qubits and controlling them. You have 2 to the 50 complex amplitudes that you can manipulate. And the point is, when you manipulate these amplitudes of this like huge state, you operate in all these amplitudes at the same time. So what quantum gives us is massive parallelism for free. That is quite different from classical computing. How we can, so at the end, as I say, what we do is to manipulate all these amplitudes, or to operate on all these states at the same time. So how do we do that? So let me show you an example of how a quantum algorithm, let's say, works. So usually, this is just an example of an algorithm that is called Grover's algorithm. And what it does is we start with an equal superposition of all the states. So all these alpha parameters, they have, let's say, the same amplitude. And by doing some magic, some unitary transformations, and some magic that is called interference, what we do is that we amplify the amplitude that contains the right result, the correct result of your algorithm, and we minimize the rest of the amplitude. So when we read out, so when we run our algorithm and we read out the result, we will obtain the correct one with higher probability than the other ones. But still, as I say, this is a, oops, sorry for that. This is a probabilistic way of computing because I will still have like a small chance to write the wrong result here. And indeed, again, it's a binary value what we get. For example, we will get 100 with high probability for this algorithm. So this means that if you want to compute something with a quantum computer, you will have to run your algorithm several times in order to make sure that you get the right result. How many times? We don't know. It's going to be 10 times, 1 million, 1,000 times. We don't know yet. Let me illustrate with an example, with a very simple example, the power of quantum computers. So imagine that you have a mess, and then you want to escape in the center. So how a classical computer will do that is that it will explore each of the paths one after the other. So you will follow each of the paths one after the other till you are capable of finding the path that brings you to the exit of the maze, right? Now, what if we have a quantum computer? In a quantum computer, by exploiting this phenomena that I just explained, superposition or entanglement, you will be capable of exploring all these paths at the same time, and therefore you will be capable of finding the exit faster than with a classical computer. That's why, again, quantum computer can be much faster than the classical ones, and we can get up to exponential speed up compared to the classical machines. What else? How do we compute in quantum computing? What kind of, let's say, circuit? So one of the most famous models of computations, and there are different ones, is the one based on circuits. And this is one of the most famous ones because we are used to that, right? We as an engineers, we reason in terms of circuits and digital design. So if you look here, looks kind of similar to what we are used to. So here is just a representation just of a quantum circuit in which each of these lines represent a qubit. So in this case, we have 4 qubits. And each of these blocks here are single qubit gates, so a Hadamard, an X, a T, whatever they do, doesn't matter. For now, and also like 2 qubit gates, this is called a CNOT gate, that as you see requires the interaction between 2 qubits, for example, in this case, between Q0 and Q2. And at the end, this is just the measurement. Something that I would like to emphasize here, and it's quite different from the classical way of computing, is that in the classical world, you have your digital system, right, your analog system, you have your design, and then for doing computation, you stream your data through the transistors and through the gates, right? And then you get the result. Here, it's a bit different. Here is the qubit that holds the state. So the qubit is your memory. And by applying the gates to your qubit and changing the state is how you perform the computation. So I like to say that quantum computing, it's a specific case of memory computing, like kind of memristors, so these kind of technologies. Okay, so far I have been talking about how wonderful quantum computing could be, right, and good news, but of course there are also bad news. And the bad news is that qubits and gates are error-prone. So qubits are very fragile. That means that they lose very easy their information just because of the interaction with the environment. That is what is called decoherence. And that decoherence can go from microseconds up to seconds, depending on the technology. And operations, so these gates that I show here are imperfect. And nowadays we have gate error rates up to 10 to the minus 2, 10 to the minus 3. That if you compare with CMOS, that is 10 to the minus 18, 19, something like that, right? It's like, wait, there is no way to do anything meaningful with those very high error rates. That's why we need to protect quantum information in order to perform any kind of computation. And what we use is what is called quantum error correction, that I will elaborate a bit on that on the next slide. But the basic idea is like in classical error correction is to encode what is called a logical qubit that is composed by several physical qubits, so to have some kind of redundancy in your system in terms of qubits. Now, what a quantum computer is not and what it is. So a quantum computer will not be a replacement of a classical computer. It's not that you are going to have at your home a quantum computer for reading your email, right, or for doing. So it will be good, but only at a specific applications, like the one that I mentioned before. So you may want to use a quantum computer, and how we envision that in the next coming years, it's a service that you will have in the cloud, and then you will pay for running an application or a difficult problem on that server, on that quantum computer. Then, as I just mentioned in the previous slide, it's just a memory kind of computing device. And a quantum computer, I don't like to call it like that, although it's the word that everybody uses, is going to be a quantum accelerator or a quantum coprocessor. So in other words, a quantum computer will be working together the main host, or the host CPU, and some of the tasks will be thrown to your quantum accelerator. So nowadays, we are in this heterogeneous multi-core architecture routine, right, in which you have your main CPU that connects to different accelerators like FPGA, GPUs, TPUs, so why not to have a quantum accelerator there? So it's the same kind of paradigm of computation. Now, the idea of building a quantum computer is not something new. It's something that proposed Richard Feynman when he was the plenary speaker at this Physics of Computation conference back in 1981. So Feynman, he was the one that asked this kind of questions that, can physics be simulated with a universal computer? So the problem now is that we cannot simulate the quantum mechanics that reflects the nature with a classical computer. So he proposed to build a quantum computer to simulate quantum mechanics. So since then, there has been a great evolution in this field with the appearance of the first algorithms back in the 90s, being the most famous, this Shor's algorithm for factorizing large numbers and has application on encryption and decryption. Then in the late 90s, early 2000s, we had the first quantum computer based on a specific kind of computation that is called quantum annealing, that was developed by a Canadian company called D-Wave. I guess that you may have heard of that. But there is a debate here because they say, no, it's not a quantum computer because it didn't show that it can solve problems faster than a classical one. And since then till the present, we are working, or physicists, mostly physicists, are working on different ways of implementing a quantum bit that, for example, trap ions or quantum dots or Majoranas or superconducting qubits. So nowadays we have these big companies investing a lot of money on quantum. So we have Google, IBM, Intel, Alibaba, and some startups like Rigetti. And this is the number of qubits that we have in current processors, so a couple of tens of qubits. And as you may have heard, a couple of weeks ago, I think it was 3 weeks ago, that Google claimed that he demonstrated quantum supremacy. So it was in the newspaper here in Spain too, I think, right? Because there is actually in Spanish guy, Boixo, who is one of the authors of this paper and works on the quantum algorithm part. So that's a great achievement. I put here a question mark because indeed first, quantum supremacy is a term that was suggested by John Preskill from Caltech University. Afterwards, he realized that supremacy is not a very nice word, right? Because that reminds to white supremacy and other terms that are not very nice. And anyway, so you can call it quantum advantage. So they demonstrated this quantum supremacy, and that refers to the fact that a quantum computer can solve problems that a classical computer cannot. Now, I put a question mark here because I will show you first what they did. So what they did is that they built this processor here that is based on superconducting qubits. It's called Sycamore processor, and it contains 53 qubits. And they were capable of controlling or creating an state with 53 qubits. That means that they create a state space dimensional of a dimension of 2 to the 53. That is around 10 to the 16. So that's kind of, wow, impressive. You cannot do that with a classical computer. You cannot store that information in a classical computer. What they run, so what kind of algorithm they run, is not a real application. It doesn't have an application on anything. So what they do is just to create a kind of random circuit in which they alternate single qubit gates with this kind of 2 qubit gates in different layers. So by doing that, what they do is like entangle some of the qubits and having this high dimensional state space. They were capable of running this kind of circuits in this processor. By the way, I forgot to mention that here the crosses are the qubits, and these blue things are, let's say, the couplers between the qubits or the connections between them that allow them to interact. And the good thing or the new thing about this topology of this processor is that those links are reconfigurable. So you can have a qubit connected to the other or not, just like a switch there. Let's put it in that way. Anyway, so coming back to this example, is they were capable of running 1 million samples, 1 million runs of a single sample and run it in this processor in a bit more than 200 seconds. And they calculate that for doing that in a classical computer, like playing some tricks and some kind of optimization there, it will take more than 10,000 years. So this paper was published in Nature, and there was, but if you don't like to read papers and you prefer that someone else tells you the story, there is a very nice talk from Martinez explaining exactly this paper that I highly recommend you to see. And he's a great speaker, so it's very funny. Anyway, so this thing is not only about, or this experiment was not only about quantum supremacy. It was valued for two things. First, for validating the quantum computer, because a quantum computer is not only the chip, is the, let's say, the full stack that I will show later. And then it was a good way to show that quantum mechanics it's really complex. We kind of knew that, right? Then they also realized that errors, because I say that quantum hardware is very error prone, do not depend on the entanglement and the computational complexity. In other words, we thought that the more qubits you put in your system, the higher your errors will be. But it seems that it stays more or less the same kind of errors there. And then at the one nice sentence at the end of the paper is that they say that we expect that lower simulation costs that reported here in the paper will eventually be achieved. Because they were aware that other people like IBM, so the competitors, were going to say, hey, wait, that's not right. And that's exactly what IBM did 2 days later, that they say, hey, we argue that an ideal simulation, so you can simulate that in a classical computer with doing the same task, in a classical system, can be performed in 2.5 days and with higher reliability. So that's not quantum supremacy, so you cannot claim that, okay? Yeah, because we are in this, like, I would like to say, I can say that, a stupid competition, right, between big companies to see who has more qubits, who demonstrates quantum supremacy. Okay, let's see. Anyway, it was like a big step in our community. So something that Martinez also mentioned in his talk is that he says that this is the beginning of the NISQ era. NISQ stands for Noisy Intermediate Scale Quantum Technology. And this was a term, again, that was introduced 2 years ago, by John Perskill. But this is a nicer word, right? So here he was okay. So he doesn't have to change the term. This is okay. And intermediate scales refers to the size of your quantum processor, so how many qubits you have in your processor. And noisy emphasizes the fact that you have these unwanted interactions between the qubits and the environment. And because of the low number of qubits, and especially because of this noise, they will place serious limitation in the kind of applications that we will be able to run in the next years. In other words, that in the next years, we will be able to run only very kind of small or simple algorithms or circuits if you want to have like a meaningful computation or meaningful result. So, as I mentioned, there are different ways of building qubits. So there are different technologies that are being explored. This is a report from BCG, so Boston Consulting Group, that I really also recommend to read if you are interested in quantum, because they show this table. So those are the different technologies. It's really blurry red. You cannot see it. Anyway, there are different technologies that are being investigated. So we have superconducting qubits and trapped ions. Those are the most promising right now, because they were able to put, let's say, more qubits on a single processor. But there are other ways of implementing qubits, like, for example, photonic qubits, or silicon-based qubits, or topological qubits. Some of the properties that they mention here is the qubit lifetime that has to do with the decoherence, so the fact that a qubit loses its state just because of the interaction with the environment. And those times go from microseconds, for example, in superconducting qubits, up to seconds in silicon spin qubits. Other things that they mention here is the gate fidelity, so how well you can perform your gate in your circuit. And another important term is what they call connectivity. In other words, so how qubits are connected in your chip. Right? Before I showed the Google chip, that they have this kind of 2D array with nearest neighbor interaction, and that you can connect qubits in different ways, as I will show in next slide. Now, they also have this very nice graph that you cannot see, but I will try to explain, in which, okay, good, in which they show what is the exponential speed up that we can get versus the robustness of your algorithm. So here you can there are some algorithms like the Shor's algorithm that I mentioned for encryption decryption, or the HHAL that is used for solving a linear solver, and they can have an exponential speed up if you compare to the classical counterpart, but they are really far away. For being able of running those kinds of algorithms, we will need like millions of qubits and to use quantum error correction. So, and we are talking about now 70 qubits. So no way, we still have to wait like more than a couple of years, I will say. But what we are now, what we will be able to run with these NIST processors is this kind of algorithms here that are kind of robust to noise, and they have the main application in optimization. So this is what is called, for example, variational quantum eigensolver, or QAOA, that is for quantum optimization. And the idea, that, as I mentioned before, is to use a hybrid approach in which you have a classical processor and a quantum processor working together in order to solve, or to solve an optimization problem. So in the classical part, you recalculate some parts, some parameters, you throw it to the quantum part, and goes back, and in this loop till you get kind of good enough solution for that. Now, so far I've been talking, so I just gave an overview, so where we are, what are the main companies, and I've been talking a bit about the quantum technologies in the last 2 slides, about the quantum algorithms. But as you may know, if we want to build a quantum computer, it's not only about building or developing applications and building quantum processors, it's about developing an entire system, or what we call the system stack. So, and this is exactly what we are doing at QDEL. What we are doing is to close the gap between quantum applications and the quantum processors. So if you look at this picture and you look at the different layers of abstraction, and you are a bit familiar with the, let's say, the architecture of a classical computer, you will say, okay, wait, if I look at this picture, I see exactly the same layers than in a classical computer, just with a Q before the name. And I will say, yeah, you are right. That's what we did. But we don't have better solution right now, so what we do, right, as an engineer, is we take the approaches that we use in classical computing, and we try to apply them to quantum, with some changes there, right? And so far, so good. I'm not claiming that this is the best approach, but this is the approach that we are taking right now. Maybe someone comes with something much better, okay? Good. Anyway, so what we need for building a quantum system is, and the things that we work on is like, in order to express your algorithm, you need a high-level programming language. That can be, for example, C++ or Python, because the physicists like more Python than C++, fine. Then you need a compiler to translate this high-level programming language into a series of instructions, or machine code that your machine is capable to understand, and to define, of course, an instruction set architecture. And through your mark architecture, you translate these instructions in a series of pulses that control your qubits. Because at the end, a gate in your qubits, so in a real qubit, how you perform a gate is by sending a microwave. For example, in superconducting qubit, you send a microwave signal with a specific amplitude, envelope, and frequency. Okay? So, and I guess that it's clear from this picture that in order to develop this kind of system, we require contributions from different scientific domains, such as physics, computer science, mathematics, electrical and computer engineering. So this is also a call to you, to this community, to be involved in this field of research, because there are plenty of challenges there. And to be honest, most of the challenges that we have right now are not related to physics, are related to engineering. So, just to be, a bit more concrete about this stack, as I mentioned, we need a high-level programming language to describe your algorithm. Imagine that this is just an entanglement thing. There are different programming languages and compilers available right now in the quantum community. That, for example, we have the OpenQL that we develop at TU Delft in QTech. You have the Quantum Development Kit from Microsoft, or one of the most famous one that is this QuizKit from IBM. Because as you may know, IBM already have some small quantum processors in the cloud, and they are accessible. So if you Google IBM Quantum Experience, then you can go to their website and run like very small circuits there for free. And there are other versions and larger, but for those you have to pay. Anyway, so there are different programming languages and compilers, and at the end, when your, let's say, algorithm is described in this kind of circuit, and your compiler translated again in a series of pulses that are sent to your qubits, that are those two black dots here, to your qubits in your quantum processor. So how does it look in reality? So this is our quantum computer or kind of quantum computer in QTech. So something that I didn't mention is some of the quantum technologies, they work at very low temperatures. And when I say very low temperatures, I'm talking about 20 millikelvins, so that's close to zero. So here's our quantum processors based on superconducting qubits. This is with 2 qubits. This is the other one that is, I think it's 17 or 49. I'm not so sure. But this was built, for example, in collaboration with Intel, because what we do with Intel is we build our own samples in QTech, but they also build their own samples in Intel, and they send it to QTech that they characterize them. Anyway, so these processors, they work at low temperatures, 20 millikelvins. So they are in this cryostat. So these cryostats have different temperature stages, and they are placed here in the coldest place. And this cryostat is inside this big fridge. It's a fridge like taller than me. And this fridge is in the ground floor of QTech. And you have these cables here, right? Because those are the cables going to the first floor in which we have the electronics in order to control the qubits. Because as I said, in order to perform computation, what you do is to send such signal to your qubits using like classical instruments like AWGs and this kind of devices. So something that we developed for this kind of experiments is what we call the control box, or microarchitecture, that what it does basically is say, you AWG1 or instrument 1 send this pulse to this qubit at this time. It's like kind of orchestrating the sending of the pulses. And yeah, and for that we won one of the best papers in this micro conference a couple of years ago. Now, what are the main challenges in this full stack, in these different layers from going from the quantum algorithms up to your quantum chip? So the first challenge starts with the quantum device, that, as I mentioned, we need to enhance the decoherence, so to have qubits that can hold the state for a longer time. And we also need to improve the fidelity of the operation and also the scalability of the chips. The second challenge is regarding the control electronics, because right now we have the control electronics at room temperature, and we have all these cables going from room temperature to 20 millikelvins, but that's not a feasible approach. So some of my colleagues, Fabio Sebastiano, is working on putting these classical electronics next to your qubit, let's say at 4 Kelvin. And for that, they are developing like models, for example, SPICE models, together with Andrei Vladimirescu, the father of SPICE. So they are developing cryo models for that. And now, the third challenge is the one that we are mostly working on, that is to bridge the gap between your quantum applications and your quantum chip, or in other words, the compilation of quantum circuits. So in the next slide, I still have time? Yeah, okay, yeah. In the next slides, I will be a bit more technical, and I will focus on two things that we are doing in our group, that is the compilation of quantum circuits and the fault tolerance or the quantum error correction in this kind, in these devices, in this kind of small processors. So what is the compilation of quantum circuits? This is also known as the mapping of quantum circuits. So the compilation is not only about generating, let's say, the instructions or the machine code that your processor is capable to understand. It's also about transforming the circuit to satisfy the constraints of your quantum chip. So let me illustrate this with an example. Imagine that I have this quantum circuit here. So I have here 7 qubits from Q0 to Q6, and those are single qubit gates and 2 qubit gates that require, so as I mentioned before, a 2 qubit gate requires the interaction between 2 qubits. And imagine that I want to run this kind of circuit in this chip, in which each of the dots is a qubit, let's say, and each of the H's is the connection between qubits, or in other words, the interaction between qubits. So in this qubit, for example, can interact with this, that, and that, but this qubit cannot interact with that one, because there is no connection between them. So the first thing that I need to do, for example, when I want to run the circuit is, okay, I can just perform one operation after the other, but as you may know, that's not efficient, right? So you want to be able to parallelize operations and do as many things as possible in parallel, right? Especially when you go to hardware. And in this case, it's even a stronger requirement because we are limited by the coherence time of the qubit. So you have to do computations fast enough before your qubit decoheres and lost the information. So this is crucial. The other thing is like, okay, I have here my 7 qubits from Q0 to Q7, and those are what we call virtual qubits or program qubits. Where to place those qubits in the physical device? So you can do it in like, say, random way. Let's say Q0 goes here, Q1 goes there, Q2 goes there, just in a normal way. Or say, okay, wait, I can look at what qubits need to interact afterwards and do a kind of optimal initial placement. In other words, like to place the qubits that need to interact a lot already close to each other, right? That they share the connection between them. And this is exactly what we do in this example. But you cannot put all the qubits that need to interact close to each other from the beginning. So in other words, there will be qubits that will be far away, and then you will have to bring them together in some way to allow them to interact. So just look at this example and look at this C naught. So those are the interactions, let's say, which is 0 and 5 and 2 and 3. If I look here, maybe you cannot see that. 0 is here and 5 is there. So there is no way to do that operation between them. And if I look at 2 and 3, so 2 is here and 3 is there, so they cannot interact neither. So what we do is to move quantum information in order to bring qubits together. So there is a kind of gate that is called a swap gate, that what it does, it is to exchange the state between those two qubits. So by doing these swap operations, I can bring, for example, between those two, I can bring those qubits together, and now, for example, 2 and 5, no, sorry, 2, what was that? It was 5 and 0. 5 and 0 are together, they can already interact. So this is what we call, by inserting these swap operations, we can move quantum information. We say qubits around, qubits stay in the same place, where you move the information that they carry, and you can move information around. This is known like the routing of qubits. The problem here is that the more operations that you add to your system, the longer your circuit becomes, and also the higher the probability of introducing an error in your system. In other words, so by adding these swaps, you decrease the success rate of your algorithm. So you have to be very careful how to do that. So there are other hardware constraints that we have to consider, not only the connectivity, but there is something that's called elementary gate set. So in other words, you cannot perform any gate in your processor. So each processor has what is called elementary gate set, and those are the gates that you can perform or are supported by this processor. Therefore, you have to decompose any kind of gate that you have in your circuit. You have to decompose it in the gates that your processor is capable to run or to support. And there are other constraints coming from the classical control, so how, let's say, the AWGs are connected, and that has an impact in what operations can be performed in parallel, and other crosstalk problems there. And here, just have an example of the different layouts of different chips that are being developed. So this, for example, this is, let's say, the connectivity graph, or the kind of layout for one of the IBM chips. This is also one that they are planning to build. This is the layout of a chip that we built in QTech that is called Surface 17, and this is another one from Rigetti. So this problem of mapping a quantum circuit into your quantum chip is an NP-complete constraint optimization problem, and to solve that, there are different solutions that are being posed. So the main approach is to use heuristic search to look for this initial placement and then to do the routing, but there are alternative approaches based on AI, right? AI can solve almost everything, I think. Whenever you have a problem, you don't have to solve it, just use the AI. I'm kidding. It's a very powerful thing, right? So here we can also use AI. So what is the cost function, or what is the parameter that you want to optimize when in this kind of problem? So the cost function that we use, of course, is the number of gates, because as I say, the more gates you add in your circuit, the higher the probability of introducing an error. So you want to minimize that. The circuit depth, that is basically the number of stages in your circuit, so the latency, let's say, of your circuit. But at the end, what you care about, it's about the success rate of the algorithm. Because again, when you increase the number of gates, and when you increase the circuit depth, where you are decreasing is the success rate of your algorithm, because you are adding more gates and having a larger execution time, let's say. So there is a nice paper that was published by from Princeton University with Margaret Martinosi's group, in which they developed, let's say, a compiler to run and to be able to run an algorithm on different kind of chips. That you can see the topologies, and they focus on they use as a cost optimization metric. The reliability between the links of one of the IBM chips. So this is the variation between these connections between the links of the C nodes of different between different pairs of qubits in one of the IBM chips, and you can see the variation among the dates, and it can vary in between the links, and it can vary up to 9 times. They also run these algorithms, again, in these different processors, and they obtain the success rate. And of course, they run it, for example, in a processor from based on ion trap, that they have full connectivity, so all qubits are connected, so you don't have to move any information, and of course, they get higher reliability in this kind of processors. One thing that they claim is that they have a compiler, let's say, or a mapping that can be used for any kind of chip, and I will argue that that's not completely true. And I will tell you why, because we did something similar, so we just published a paper, so it was, I think, last summer, we published a paper with this kind of compiler in which we do this initial placement, routing, and scheduling based on and we map different algorithms on one of the IBM chips and one of the chips at TU Delft. And how we did that, we also claim that it's kind of universal, because you can have a configuration file in which you describe the parameters. So in other words, if you change, let's say, your chip, you only have to change the description in your configuration file. But what we also observe is by running the same, or trying to run the same kind of algorithms on a different processor with different technology, so those processors are based on superconducting qubits, and these ones are based on silicon spin qubits, it was not enough just to change the configuration file, but we also had to change some of the techniques that we were using in the router itself. Because the way that you move information in this kind, and I don't want to go into the detail, but the way that you move information in this silicon spin qubit processor is different than from the other one. So here, let's say, universal solutions are not that flexible or not that universal, at least not right now, in which we are looking at different technologies. So, but still, there are some people that say, okay, so instead of having like a machine-specific compiler tool, that is what we did, and the people, for example, from Princeton and also from the University of Chicago did, why not to have like a general-purpose compiler that is capable of addressing different hardware constraints? And this is based on temporal planners, that is kind of AI, that the only thing is that you have to input the problem, and then you have a black box let's say, that solve the problem for you. So just to summarize this part, so we need efficient mapping strategies to map, let's say, or to be able to run your algorithms on these processors that we have nowadays, and also the ones that will have in the future, sorry. And that will depend not only how efficient they are, will depend not only on the characteristics of the algorithm, but also on the characteristics of your quantum processor. Then you can go for two approaches. You can have a technology-specific compiler or a more general approach. But we still need to define metrics based, for example, on reliability. And so far, the approach that we have been taking is bottom-up. So it's whatever chip, let's say, the physicists are able to produce, we try to map and to optimize all our algorithms for that kind of chip. Now, let me change a bit gears here and talk about something that is called fault-tolerant computation based on quantum error correction. As I mentioned, qubits and operations are error-prone, and in order to perform any manifold computation in quantum, we need to use quantum error correction. So what is quantum error correction about? So quantum error correction is based on classical error correction. So in classical, what we do is to encode your bit, usually in an odd copies of bits, right? So one bit is encoded, let's say, in 3 bits. And then you detect errors by doing majority voting. So if there was a flipping one qubit, by doing majority voting at the end, you say, okay, there was a bit flipped on the first, sorry, not qubit bit, it was a bit flipped on the first bit. In quantum, we use a similar approach. So we also do encoding. So a physical qubit, each encode, for example, in this case, is something that is called logical qubit, and is composed by 3 physical qubits. How we encode information is not by copying the qubit, because there is something that is called the non-cloning theorem. That means that quantum information cannot be copied. So in order to do this logical qubit, we do it through entanglement, so using these CNOT gates, whatever that means. Now, how can we detect errors? We cannot measure all the information in order to see there was an error there, because we destroyed the superposition. So how we do that is by using some extra qubits that are called ancilla qubits, that are kind of helpers. And what they do is by doing these parity check measurements, they look at the parity between the different qubits, and they can, and by measuring them out, we can look if there was an error in which qubit and what kind of error. So at the end, when you measure the out, I put here +1, -1. Those are eigenvalues. So physicists also like eigenvalues. We can say 0 and 1. Okay? So one of the most promising, I think I'm running out of time, right? Anyway, so, no, well, we have the coffee break afterwards, right? If it's a bit shorter, right? Okay. Yeah, 10 minutes, okay, good. So one of the most promising quantum error correction codes that we have nowadays is called surface code, and it has this kind of a structure in which each of these white dots are the data qubits, so the qubits that hold information, and these green and red dots are the ancilla qubits that are only used for detecting errors doing these indirect measurements. And we have two kind of qubits because we need to detect 2 kinds of errors that are called bit flip and phase flip. Yeah? So at the end, as I said, what you do is to measure out the ancilla qubits, and you get this kind of set of +1 or -1, and send this information to an error decoder that is just a classical block in which what you run is a classical algorithm that is called minimum weight perfect matching. So with this information, when you construct this kind of 3D graph in which you have to match this +1 or -1, you have to match them in space, but also in time. And by doing this matching, you can detect or you can identify errors. So you can detect what kind of error had happened and in which qubit. The problem of this approach, of this minimum weight perfect matching algorithm, also known as Blossom, is that it scales polynomially with the number of qubits, and it also scales polynomially with the error rate of your physical qubits. So what we propose, or an approach that we are taking at TU Delft and also in other universities, is to use neural networks to do this decoding process. So what we do is that, so the good thing about the neural network is that the execution time or the detection of errors is constant after being trained in spite of so it's independent from the physical error rate, and also it scales linearly with the number of qubits. So it's more scalable than the previous approach. Yeah. So this surface code is a very promising quantum error correction code, but the bad news about this code is that it requires a high number of qubits just to encode information. So just to give you an idea, a logical qubit can consist of maybe 10,000 qubits, physical qubits, right? And we are far away from that, so no way to implement that quantum error correction nowadays. So what we are doing right now in these NICs devices, again, in which we are limited by noise and we are limited by the number of qubits, is to use error mitigation of passive error correction. In this case, you don't encode your information, so you don't need extra qubits. What you do, it's a software level. So in your compiler, let's say, you play some tricks there, so you change some gates for others that produce less errors or cancel the errors in your system, right? But still, it's time now for demonstrating that we can perform fault-tolerant quantum computation, and for that, there are really like some layouts that use this kind of layout for surface code, like the one that we are developing at QDEL, the Surface 17, also at IBM, and also this is IBM, yeah, and this is also IBM, and this is, again, our group. So we are still trying to demonstrate these concepts in the devices that we have nowadays. Now, in the two things that I explained, I mean, the more technical things about mapping of quantum circuits, or compilation of quantum circuits, and quantum error correction, what we are taking is a bottom-up approach. In other words, so the physicists are giving us whatever they build, that is wonderful, they cannot complain, and we're just trying to map things there or to perform fault-tolerant computation on those devices. But then the question is, why not to take not only like a bottom-up approach, so also a top-down approach across layers? So why not to perform a design space exploration across layers in order, and by doing that, what that will allow us is to optimize this full stack for a specific technology or application, or even to provide some hardware design guidelines to the physicists to say, hey, physicist, if you change this connection here, the reliability of your algorithm improves by 80%, for instance. I'm just inventing here. Or what will also allow is to benchmark different technologies, because as I just mentioned, we are now exploring, we are in the phase in which we have different technologies and we don't know which one will be the winner. And we can also perform, for instance, scalability analysis. What if we have thousands of qubits? How that will affect the full stack, and what is the best strategy there? Now, 5 more minutes. Yeah? I would like to finish my presentation with a very hot topic, and it's the, let's say, how to say that? How to say that word? The intersection. The intersection between two worlds, that is the machine learning and the quantum world. So there is a very exciting field of research that is called quantum machine learning. And quantum machine learning can have different meanings. So one meaning is to apply machine learning to quantum. So they are applying already machine learning techniques in order to prove, for example, the fidelity of your gates or some quantum-related processes in your processor. You can also apply quantum to machine learning, so to have a quantum version of your machine learning algorithm that is faster than the classical one, or use machine learning for related problems, like for example, the one that I show in error decoding, that we use neural networks to identify the errors, or for routing the qubits, for this thing about moving the qubits around, right? Now, let me show you just a couple of papers. So there is a very interesting paper that was published a couple of years ago by Viamonte that gives a very nice overview about what speedups we can get by building a quantum machine learning algorithm. The machine learning is very good at creating input-output high-dimensional data sets, and for that classifying some functions. So here in these tables, you can see different architectural implementations for machine learning based on Bayes interference or the perceptron. But I would like to emphasize that the SVM. That is because it's very similar with the topology of the kind of topology that we have on quantum, that you have a high dimensional space, and at the end what you get is a single value. So this is the kind of theoretical speed ups if you compare with the classical counterparts that you can get. But the main bottleneck comes when you try to implement those algorithms. So the most difficult part is how to input your data in your system. So because usually you have classical data that you have to encode in quantum data and provide it to your let's say, quantum machine learning device. Also, it's about the output problem, because at the end you generate like a super large bit strings that you have to send back to your classical part. Also about the cost of the problem, because they don't know yet what kind of circuits you will need in terms of what size of your circuit, so number of qubits, a number of gates, so how big the problem will be. And also related to these other problems is about the benchmarking. So they don't have, let's say, a good metric to compare the classical counterpart with the quantum version of your algorithm. There was also, like, published this year, a very interesting approach that is it's already using in conventional machine learning, that is something called learning to learn. And that's about getting the metaparameters for high-dimensional networks. So what they do is use two neural networks, one for calculating, let's say, the metaparameters, and the other for implementing them. They use the same approach in this paper, but in this case, they use a classical recurrent neural network to learn the metaparameters from the application, and then the quantum neural network to implement them. So it's something that, again, it's something very, very novel in the classical machine learning field that is also being applied. There are some quantum ideas there. So just to finalize the presentation, I would like to give some hints or some vision about machine learning. So the first one, it's about the metrics that we use in machine learning. So in machine learning, one of the main bottlenecks, or one of the main metrics is not the performance, but also the energy consumption. So why not to have something similar for quantum machine learning and call it quantum green volume? So I forgot to mention that quantum volume, it's a metric that was proposed for benchmarking, let's say, the quantum processors by IBM. So why not to have like something similar for machine learning? Now, one of the main bottlenecks in machine learning is the data movement, right? And as I mentioned at the beginning, quantum computing can be seen as an in-memory computing device. So why not to use this property in order to avoid this bottleneck and this movement of data around your system? The other one, and it's in the same lines, it's about the communication needs. So if we build, let's say, a quantum machine learning coprocessor, we have to look at local and global strategies for communication. And why not? So we have also machine learning, this intermediate hybrid, with this approach, and we have clusters. So why not to put in these clusters, why not to put like a NIST processor there together with your classical cluster, let's say. And finally, there is also like a concept that is being used in machine learning that is called self-healing. That is, within your machine learning algorithm, you learn about the non-linearities of the system, you learn for that, and then you self-heal or you correct for that. Why not to do the same for the quantum machine learning, as we know that the technology is very error-prone? Why not kind of incorporate that kind of self-healing in your machine learning quantum algorithm? So with that, I would like to finish my presentation, and of course, I would like to acknowledge my team at TUDELF, so the technical people, the PhD students, as well the master students that are working together with me, because as you know, they are the main drivers of our research, so I'm really thankful to them. Talking about appreciation and recognition, I would like to take this opportunity to thank one of the persons who opened the doors to me to research and who was my PhD supervisor. So, yeah. So I would like to do it here because, I mean, it's a very well-known person in this community and an esteemed person. So it's Antonio Rubio. And back then we were working on something completely different, right? But he challenged me and he shared with me the enthusiasm for research. So, gracias, Antonio. And yeah, back to quantum. I'm open for questions.
good morning. Thank you for your nice presentation, very inspiring talk about this hot topic. I have indeed a question related to the physical issues. No, you mentioned that you're now it's more than an engineering work than the physics work. Probably you are right, but I'm wondering about indeed the working temperature that you mentioned something in your some of your slides, no? That as you know better than me, that working the operating temperature for this kind of computation is very low, really low, no? So this is a challenge, and you need usually big infrastructures, and probably this is behind why the number of qubits it's still low. Even so, this with a low number of qubits, you can do many things, and you can achieve the quantum supremacy, as you mentioned, no? But I'm wondering, my question is, it's about from your experience, it's about the emerging materials and the emerging technologies. If you feel, from your experience working on this kind of it's fascinating work, if you feel that the evolution of this kind of computation will follow the same trajectory as the classical computation. For instance, when I was attending your presentation, I was thinking of the initial stage, I mean, of the classical computation, the big computers that, you know, by the size of these big computers were in the size of a building, no? Sometimes. So now you need a big infrastructure in order to keep the temperature low. So I wonder if for some reason you find some research on new materials, emerging technologies in order to make these quantum bits operate at, I will not say maybe room temperature, but not so low temperature, no? So that you will not need in the near future so big or so, you know, this let's say complex infrastructure in order to make this computing work. Okay, thank you.
Hi, yeah, thanks for your question. Indeed, very interesting question. So, yeah, so indeed, one of the main problems of making this system scalable is that they need to work at very low temperatures. And on top of that, for example, superconducting qubits are pretty big if you compare with other technologies, so they are in terms of microns. So, yeah, there are some, and the problem is that the control electronics, right, that you have to bring all these cables for very low temperatures, so it's not about only the fridge, you have to bring those things. So as I say, there are people already working on moving the control electronics down to, let's say, cooler temperatures, but there are also proposals of some kind of qubits based on quantum dots to build what they call hot qubits. Hot qubits is to bring the qubits from 20 millikelvins to 4 kelvins. It's not the still room temperature, but with higher at least, right? Like how we going something there? Okay, it sounds like stupid, but it's not, right? So those are the kind of materials, and in terms of materials, what they are looking, because now they are more concerned, let's say, about the quality of the qubits, than about the scalability, or it's both things. So, for example, for building these silicon spin qubits, they were looking at material like silicon germanium. So I can see similarities between quantum and the way that we did it in the past with classical CMOS, in which is materials, which is structures, in order to scale up, to have more qubits in your system. But indeed, the killer is the difference temperature between the electronics and your device. There are other technologies that they work at low temperature, like the optical, the based on optical phenomena, but still they are not scalable neither, because all the infrastructure that you need for controlling them. I just don't want to ask, okay.
Thank you very much for your really very nice talk, and really enlightening. And you have mentioned on your talk that big companies like Google, Microsoft, IBM, they are in this race. I have one curiosity, is what is the business model regarding quantum computing? Why these big companies, they are investing big amounts of money in this research? I'm just curious to know that, if you can comment on that. Thank you very much.
You want the truth or the polite answer and the correct one? Yes, you can choose. I can be very honest here because I work with Intel, so I can tell from my own experience, okay? So how that happened that with Intel is that Intel suddenly realized that all the big companies were investing in quantum, and say, wait, we are ahead, right? So we need to invest. We have to do something. Okay, so how this happens, for example, is the head of our research, so the responsible of quantum computing at Intel in Portland, so he started traveling around, visiting the main centers working on quantum technologies. And in this trip, he passed by Delft, and then we have a meeting with him in which we explain what we were doing there, whatever, and he went to Australia, to all around the world. So, for example, one of the main reasons that they decided to collaborate with us and to invest on quantum there is because we told not only about the qubits, because most of the places focuses only on the technology, but we also talk about building an entire system. We focus on compilers and on the higher layers. That makes sense, right? Yeah, but physicists at that time, they think, okay, and I'm not saying that they are good, but they say, okay, we have the processor, it's done. No, it's not only about the qubits, right? So they really appreciate that. Now, how we work with them, as I say, is that, for example, we build our samples in Delft, they build their samples in Intel, and then they send them to Delft to characterize them. But what we are seeing after 5-6 years, this is the 6 years that we are working with them, is that first, some of our students that finish, or even technical people, they go to Intel there, so they hire that people for their team, because they are already working on that, and then they start building their own facilities there. So they are building qubits, and of course, I mean, they have more money than us, right, so they have they can manufacture like huge amount, and especially for silicon spin qubits, because they are familiar with CMOS, so they are putting more, let's say, so what they are gaining, let's say, from us is the know-how, the knowledge. So this is what they invest. Other companies, so Microsoft, for example, has a similar model. They have their own team also in Seattle, and they also have what they say Q stations in different parts. And I guess that the models should be kind of different there. And IBM, for example, I think that they give some money to small, let's say, startups or small universities, but they really have like a big, so in terms of team and people in the company working on quantum, I think that IBM is the one, and Google, the one that have the biggest team. And for example, the Google team, this Martinez, he was a professor in University of Santa Clara, and they, let's say, they bought the team and bring it to Google. So that's the business model that they are using right now. I don't know if that clarifies, that answered your question?
Yeah, but let's imagine that we are in 2040, 2050, okay. 30 years from now. And do we have use cases, requirements for those use cases? Because I guess people there, the executive of the companies, they would know how to make money of this.
Yeah, of course. So they are also looking at
how can we make money of all this?
Yeah, they are also
systems?
looking at applications. And they have, for example, IBM, they have this quantum experience, but for example, they have this System 1, that it's let's say a quantum computer with 20 qubits, in which some people can have access and run their problems there. So the business model that I think that they are looking for is to have their own quantum computer, and then big companies will buy a time of computation in your quantum computer to solve this kind of optimization. And for that, of course, they are also looking at applications. Right. So what kind of problems? So this thing about supremacy is just the first thing, but what they are looking at is algorithms that can solve some problems that the companies have nowadays.
Right.
Yeah, that's you never know which Chinese. So, but because, yeah.
Disruptive technology that whomever wins the race, they have monopoly. And anyhow, yeah, so Professor.
So thank you for the nice presentation. You know, I come from a test background, so my question is about how do you validate the model? So imagine that you have a quantum computer, you submit a problem, you get some result. Now, how can you tell this is a correct result or that this is a fake result because something went wrong and, well, you get some number? One of the big things about classical computers is that they are mostly reliable, deterministic, and there's another interesting property. They can simulate themselves on the same technology. Okay, that's why we can validate those models. Now, apparently, if I'm not mistaken, there are some hidden things that you cannot measure because this is the physics of quantum mechanics. So now, actually, when you read, you destroy the superposition. Mm-hmm. So how can you tell that your model is correct?
So at the end, thanks for your question. So at the end, what you care about is about the result, right? And as I said, in order to make sure that you get the right result, you will have to run your algorithm several times. And if you run it, I don't know, 10,000 times, 80%, so likely 90% of the time, you will get what is supposed to be the correct result, right? So how they validate it or not, for example, the experiment with quantum supremacy is that they run it in a classical computer up to the point that they couldn't run it anymore. But imagine that you want to factorize a last number. That's the most famous example, right? The point is that you cannot factorize the last number, so to decompose it in the prime number using a classical computer. You can do it with a quantum computer, get the numbers, and then multiply them with a classical one, right? And if that gives you the previous number, then the result is just a very simple example. But this is the kind of validation that they are thinking about right now. I don't know if in the future we will have because I hope that the technology will improve, right? And we'll have lower error rates as we have now in CMOS, and if not, we will use quantum error correction. So maybe you can imagine even with the same computer as we do nowadays to validate your result. Or not, I cannot, so it's a bit of question mark there, right? We are not still there, let's say, but yeah, we have to think about that. So, yeah. No, poor guys, no. So it, yeah. 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 Right. Yeah.
Thank you. Please enjoy your coffee. I think the speech deserved a short delay, so if Chairman agree, we can start 10 minutes later, because so far we have scheduled quite well. Thank you.